Welcome to The Explainer. You've probably written or seen a line of code and thought, yeah, that makes sense. But have you ever stopped to think about how that line of code, something a human can read, gets turned into a language a computer can actually run? Well, today we're pulling back the curtain on the compiler. It's the ingenious and honestly brilliant process that makes all of modern computing possible. All right, let's just dive right in with an example. You see this line of code on the screen? To us, it's just basic algebra, right? Super straightforward. But to a computer's processor, which only gets ones and zeros, this is absolute nonsense. It's a completely foreign language. So how in the world do we bridge that gap? And that really is the heart of the problem. We humans use what are called high-level languages. Think Python or C++ or Java. They're designed for our brains to work with. But computers, they speak low-level machine code designed for hardware to execute at, mind-boggling speeds. They're two totally different worlds. So you need a translator. And not just any translator. You need an incredibly sophisticated one. And that translator? That's the compiler. The best way to think about it, at least for this explainer, is to imagine it's a factory. Our source code, that line of algebra, is the raw material that goes in one end. And a finished, ready-to-run program is the polished product that rolls out the other side. So here's the floor plan for our factory. It's basically an assembly line. Our code is going to move through each one of these stages, and at every step, it gets transformed and refined, bringing it just a little bit closer to something the machine can finally understand. So come on, let's take a walk down the line. Okay, so first up, we're entering what's called the front end of the factory. Now, the goal here isn't to build anything yet, not at all. The only job in this section is to figure out what our blueprint, our source code, is actually saying. It's all about understanding. When our code first arrives at the factory, you have to realize it's nothing special. It's just a long stream of characters, P-O-S-I-T-I-O-N, equals sign, and so on. The very first machine on this assembly line has to make sense of this jumble of letters, numbers, and symbols. This first machine performs lexical analysis. It's often called a scanner. And what it does is it reads the raw text, the actual words like position, which are called lexemes, and it groups them into categories called tokens. So position becomes an identifier. The equal sign becomes an assignment operator. 60 becomes a number. You can think of it like sorting a big pile of Legos into bins by color and shape before you even start building. With all our parts sorted into the right bins, the next station, the syntax analyzer, starts to assemble them. It builds this incredible structure called an abstract syntax tree, or AST. Now, this isn't just a list of parts anymore. No, this is a real blueprint. It shows exactly how everything is related, and it makes sure our code follows the rules of the language. Like making sure every open parenthesis has a matching closed parenthesis. This whole front-end section is basically our quality control department. After it checks the grammar, the syntax, the semantic analyzer steps in to check if the blueprint actually makes any logical sense. It catches things that might be grammatically perfect, but are complete nonsense, like trying to add the word hello to the number 5. This is the stage that saves us from countless bugs and crashes later on. All right, our blueprint has passed QC with flying colors. It's been checked, it's been verified. Now finally we can move to the back end of our factory. This is where the real construction starts. But here's a really clever part. The factory doesn't just jump straight to building for one specific computer chip. First, it translates our blueprint into a generic, universal language called intermediate code. This is such a key idea because it means you can take the same front end that understands C++ and pair it with different back ends. That's how the same code can eventually run on your iPhone, your Windows laptop, or some giant supercomputer. And look at this. You can see how our original single line of code gets broken down into this intermediate form. It's now a simple step-by-step recipe that any machine could follow. Step 1, multiply rate by 60 and call that result T1. Step 2, add initial to T1 and call that T2. And finally, step 3, make position equal to T2. It's simple, it's clear, there's no ambiguity. We're getting close to the end of the line, and now we've reached what is, frankly, the most amazing part of the whole factory. This is the optimization stage. This is where master craftspeople step in to take perfectly good code and make it exceptionally fast and efficient. The authors of the legendary Dragon book, it's the book on compilers, put it perfectly. Optimization isn't about finding some magical, perfect version of the code. It's about making smart, practical improvements. It's about finding ways to produce code that's just plain better and faster than the most obvious, straightforward version. And here is a fantastic example of that. Look at the code on the left. We do a calculation, and we store the result in A. Then, what's the very next instruction? We load that exact same value right back from A. It's totally redundant. The optimizer is smart enough to see that. And if you look on the right, it just gets rid of that useless step. It's a tiny little change, but when your processor does that millions of times a second, it makes a world of difference. And this is why all this matters to you. Code optimization is the invisible magic behind almost all modern software. It's the reason your video games can run so smoothly and why your phone's battery can last all day. And after all this polishing is done, the very final step, code generation, takes this super optimized code and translates it into the specific ones and zeros that your computer's processor was built to understand. So, our finished program is out the door, but what's so incredible is that the principles of this code factory are so powerful and so fundamental that they're used in way more places than you might think. I mean, have you ever wondered how you can run some Windows apps on a Mac? That's a process called binary translation, which is basically a form of compilation. The very same techniques that check for logical errors are also used to automatically scan code for security holes. This technology is, and I'm not exaggerating, a cornerstone of our entire digital world. So at the end of the day, the compiler isn't magic. It's this beautiful, brilliant, and deeply logical process. It's an elegant factory that sits behind almost everything we do with technology, faithfully translating our human intentions into machine actions. It really is the hidden engine that powers our world. And thinking about this powerful process leaves us with a really fascinating question for the future. If these compiler factories are already so good at finding our mistakes and making our code better, how far are we from a future where they don't just translate our code, but they can actually write it for us? Now that's something to think about.